Swayam Prabha. Digital India. Educated India.
Okay, I think so. Towards the end of the last class, we came to an important step wherein we substituted the interface condition, then we got a very messy result. Okay, and I told you that it is known that S equal to m of root t. That is, what is it S equal to? That is, the melt front goes as t to the power of half. That is the assumption. Now what is the guarantee that it goes as t to the power of half? I will answer that question, but before that, assuming that S equal to m of root t satisfies that, we can substitute it into this equation 18 and proceed with the solution, right. Now can you do this? Shall we do this? Minus KL ds by dt is what? M is a constant. Okay, m is a constant which depends only on the properties. M half m t to the power of minus half, correct? Is that correct? Is it correct? Okay. Now what do we do? Is there something else which is missing? E to the power of minus, okay. Now we can collect some terms. Okay. Now we have to introduce certain dimensionless quantities. It becomes easier if we introduce those dimensionless quantities. We will introduce this now, okay, otherwise the solution becomes tedious. Yeah, so I will introduce the following. And Stefan number CPL HSL, HSL or HLS? Okay. Okay, we introduce 4 quantities now, 4 dimensionless parameters. Theta, t minus tm by tm minus t naught, maybe it is t naught minus tm is better. So T minus Tm by T naught minus Tm is the non-dimensional temperature. Eta is a similarity variable, non-dimensional variable. Mu is another non-dimensional variable which depends on m, and then the Stefan number which is CPL Tm minus T naught by HLS. So this is the Stefan number. Please recall that this is the Stefan problem. The Stefan number is very important because the Stefan number gives you the ratio of the sensible heat addition divided by the latent heat. It is a ratio of the sensible heat to the latent heat. It is a critical link between the sensible heat addition in the problem and the latent heat addition in the problem. Please remember that the latent heat addition takes place at the interface, whereas the sensible heat addition takes place only on the left side of the problem. On the right side of the melt front there is no sensible heat addition. Okay, with this we will have to play with all this and then do something to that, whatever we have done, and hopefully we will get the solution. Okay. Now we start doing, let me do the right hand side. So 2 by root pi is there, right? So I will have rho L m root t is still there, or root t must disappear, somewhere root t must disappear. Did we differentiate it properly? No. KL t minus t naught error function is 2 by root pi. What is the differential of the error function? E to the power of hang on. So error function of x equal to the differential of this will be 2 by root pi e to the power of minus eta square into the differential of the eta, right. So that term you have left out, okay. Are you getting the point? So that is why we are having trouble. So you will have km e to the power of minus s square by 4 alpha t into what is the different x by 2 root alpha t. If you differentiate, what do you get?
1 by 2 root alpha.
With respect to x, 1 by now the t is getting, now 1 by root t is getting ditch somewhere. I do not like the 1 by root 2, man. It is going, is it going? Yes, left hand side 1 by root t, right hand side 1 by root t, the 2 also gets cancelled. So what is the beauty of this? When you propose that s is equal to root of m root t, the t disappears from this equation. S already disappeared from this equation because we differentiated at x equal to s. Therefore now it is a simple equation to solve, okay. Now let us do that. So rho L HSL m by m root 2 by pi is equal to KL or KF? Four alpha f, correct? 4 alpha f into correct, because no, let's 2 by root pi, I am taking it to this side, so it will be root pi by 2, correct. What is that? Right side will be e to the power of minus m squared by 4, what is that? So Yeah, if there are some mistakes you tell me, we will fix all that. Any mistakes? Where? No, that there is a minus on both sides. No? Forget the minus. Okay. So there is a root alpha. So the 2 is still there. 2 is there or? 2 is there. Okay, let it be there. Now, how do
Cancel.
no, when you differentiated, I got this.
That is in exponent, no sir.
Into.
Okay.
This is into. Okay. No, where did I put alpha f? Okay. Now I have to introduce a Stefan number. So what I can do is, so root pi error function of mu into e to the power of mu square is that correct? Root pi mu e to the power of this e to the power of minus mu square, I am taking it to the left hand side, okay, and mu is equal to kf rho l Tm minus T naught. What is mu? M by m by 2 root alpha. M by 2 root alpha. If I root of alpha by root of alpha, if I substitute denominator and numerator, this m root alpha by 2, that becomes mu, root alpha into root alpha becomes alpha, that alpha L remains here. Okay, no mistake, no golmaal, everything is correct. Okay. Okay, some. So Stefan, see how much trouble he is giving. Huh? All this is a paper man, this paper. Okay. Now I have to bring Stefan number. So easy for me, equal to KL Tm minus T naught divided by rho L HLS, alpha is KL by rho Cp. Oh, finally we solved the Stefan problem. Okay, therefore given the Stefan number you have to solve it to find out the mu. What is mu? From mu m by root 2 alpha, alpha f is alpha L is known to you, okay. So if you find out the mu from that equation, you know the alpha L, you will get the m. What is m itself? M is s by root t. If you know the time, you will get the s. Finally, what is the goal of all this? To get s. It is such a complicated nonlinear equation. Therefore, this equation can be better used if you say, I want to get this much, I want to have this much s. You decide what is the s u, okay, for a particular time. S is equal to m root t. You decide the s, you decide the t, you will get the m. From there, you will get the mu. For that mu, you find out what Stefan number you have to use. From that Stefan number, you can find out what should be the T naught for you to get that melt front. How much heating must be applied at the left side. This is the better way to use this equation instead of, correct, instead of finding. Suppose you decide at the end of 15 minutes 12 up to 12 millimeter I want the melting, okay, peaceful. So you decide mu, everything you decide. Stefan number Cp is not under your control, HLS is not under your control, TM is not under your control, but T naught is under your control. It's T naught minus Tm. Huh? Did we make a mistake? Throughout I am writing T naught minus Tm or how? So it should be T naught minus Tm, okay, somehow you adjust that. So because otherwise Tm minus T naught will be negative, okay. So this solves this Stefan problem. What is the Neumann problem? In the Neumann problem, the Ti is less than Tm. Initially the body is at a temperature lower than the, everywhere it is at Ti. There will also be sensible heat, and you will have to consider conduction in both the liquid phase and the solid phase. So there is something called the subcooling parameter. So the Neumann problem is more general than the Stefan problem, it is more difficult to solve. The whole body is not at Tm when you start, it is at a temperature lower than, it has to be heated to that and then it will start melting. Yeah, so you have to consider conduction both in the liquid phase as well as in the solid phase, okay. That is a Neumann problem. Now we have to answer, how are we sure that S equal to m root alpha t? So consider the initial portion of cooling. That is, you are looking at the early stages, okay. So the melt has to come only up to this phase, okay. So you can say that can we say like this, I can't put equal, I can say approximately. I am assuming a linear temperature profile for the liquid portion of the interval. Am I allowed to do that? This is correct. At x equal to 0, t equal to t naught, because this will be 1. At x equal to s, this is 0, t equal to Tm. So it satisfies. Now with this approximate temperature profile, please differentiate the interface condition. So if you do this, what do you get? Minus 1 by S correct. Therefore, S ds by dt is equal to KL rho S, what is it? Is it rho L? Yes? No, don't give a blank look. So dt by dx I am differentiating from this temperature profile. Then now this is nothing but half of ds squared by dt. I can take this here, then I can integrate its ordinary differential equation in T. I can integrate now KL, rho L, HL are all properties of the medium, and T naught minus Tm is initial temperature excess, the temperature excess with respect to the boundary. Therefore, S is indeed m root T. So in the initial portion of the regime, when you are saying that the temperature profile is approximately linear, this is called the scaling analysis. You are approximately getting a scale, for this. Instead of boundary layer thickness, we call it as the melt thickness. So you have to get S equal to m of root T from scaling analysis. Now it is fundamentally correct, S equal to m of root T. Using this hypothesis, if you proceed further, you will get a relation, you will finally get a solution where you can solve for mu. It is a highly complicated in mu. Therefore, given the mu, you can work out the Stefan number and then find out how much heating is required. But the Stefan problem is infinitesimally slow heating, because the body is initially at a the Stefan problem and Neumann problem are different, because the body is initially at a temperature which is equal to Tm, everywhere it is Tm, but in the Neumann problem you can have a temperature which is different from Tm. Okay, these are the basic differences. Therefore, you have to say 1 by alpha dou T by dou tau is equal to dou square T by dou x square, both for the solid and the liquid you have to consider for the Neumann problem. Now we assume that the melt front is always like this. If this is the x direction, the melt front is proceeding vertically. This is far from the truth in many of the applications where there may be natural convection, there may be two dimensional effects and so on. The melt front may be at an angle to the x. So that is, so invariably melting will be two dimensional. So this x will be a function of x and y apart. So the x will not be a s itself is a function of time, that is one thing, and the melt front will also be two dimensional. So once you want to model those cases, you want to consider subcooling, superheating, you want to consider mushy zone and all that, the analytical solutions will break down. You have to take recourse to numerical methods. You can write your code, and so the most important thing is the capturing of this melt front. That is why we spend considerable effort now to get S. Okay, capturing this melt front as a function of time, that is a key engineering result. With that we come to an end to melting and solidification. These are the basic ideas involved. So it is tractable analytically up to a certain level of complexity. Beyond that, you have to take recourse to numerical methods. Thank you.